Well, we've made it to Chapter 9. Chapter 9 is going to have things that are very similar to Chapter 8, claims, claims about the mean, claims about the standard deviation, claims about proportion. The only difference is we're going to have two groups. So we'll have, for example, for men, what proportion are smokers? For women, what proportion are smokers? Stuff like that. What I just described are independent samples. So if I were just to say, well, look at a room and I've got two groups. How many men are there and how many women are there? That's not independent because as soon as you say, all right, in this room of 100 people, 48 are men, well, then you automatically know how many are women. That's not independent. But if you do something like I said before, we've got the men and then the women. There's two groups. Now what makes them independent is how many of the men smoke cigarettes? How many of the women smoke cigarettes? So when I find out how many men smoke cigarettes, that doesn't automatically tell me how many women smoke cigarettes. It's completely independent. That's the idea of independent samples. So we'll have two samples. Each will have an n or a sample size. X stands for how many successes, whatever you're talking about. So here's children K through 8. How many of them sleep at least 8 hours a day? And you would count. So this would be a whole number, this would be a whole number. Then you divide them to get the proportion. So this is going to be 0 point something. Likewise over here. And usually what you do is you choose sample 1 if you're given a choice. Sometimes they just tell you, here's sample 1, here's sample 2. You're not given a choice. But if you're given a choice, choose sample 1 so that P1 is the bigger percentage. I'll explain why later. All right, then the claims are going to be about P1 and P2. The claims are going to be set up just like before, except there's not going to be a number. It's just going to be, hey, I claim that P1 equals P2. I claim that P1 is bigger than or equal to P2. So we're going to have the claim, H sub 1 and H sub O, just like always. Isn't there a good looking formula here? So you take the sample percentages and subtract them. In other words, you find out what's the difference between the two groups. Then this p hat, well, that's the average of the two p-values. And what you do to find that is you add up all the successes, you add up all the sample size, and that's called the pooled. In other words, you're putting them together in a pool. The pooled estimate of P1 and P2, or the average of P1 and P2. Or you can use the calculator. Here's an example. Let's compare two very famous NBA players, LeBron James and Kobe Bryant. Who is the better three-point shooter? So what I would like to do is compare years when they were both playing at the same time. So I went back to 2007, 2008, and this is the season data. So Bryant made 150 out of 410. So that is 36.6% of the three-point shots. And LeBron James made 113 out of 359. That's slightly lower, 31.5%. So it's these numbers you look at, 36% compared to 31%. That means Bryant should be group number 1, and James should be group number 2. All right, now test the claim that they are equally good. Test the claim that they make the same proportion of three-pointers. So like always, we set up the claim, H1, it's going to be a two-tailed test, and H sub O. And like I said, notice that the claim has no number in it. You're just comparing the two groups. Are they equal? Is one better than the other? Is one worse than the other? Is one bigger than or equal to the other? Etc. So we've got a two-tailed test. As I'm sure you remember, we're using table, that's right, table A2. Whenever it is a P or a proportion, then we're using the Z table. And if it's two tails and 0.05, that's the most famous Z value. It's 1.96. So I already went ahead and drew that 1.96. And then one time I would like to do the formula. And looking at that formula, one time is plenty. So a 1.487, you can see that that would land right about here, which does not make it past 1.96, which means we did not prove anything. It's going to be failed to reject H sub O. But I would actually rather use the calculator. So what you do is go over to tests. It's the sixth one down, two proportions because it's two people, Bryant and James, and you don't have a choice, it's got to be a z-test. So then type in the data. One thing you have to watch out for is sometimes they put n first and then x, and then people will automatically put n first and then x. But on the calculator, you have to put x first, the smaller number, then n, the bigger number. X, the smaller number, n, the bigger number. And this makes it two-tailed. All right, so let's see. So you can see 3.66, that's Bryant. 3.42, that's the average of the two. 3.15, that's James. This p stands for the p-value. In other words, if you were to reject, there is a 13.6% chance you're wrong. So do not reject. Notice that the z-value is a little bit different. It says 1.490. You might think, oh, well, they're rounding. My answer is better because I used a formula. Actually, the calculator is better because right here, when we use 6.58, the calculator uses 12 decimal places. For all of these decimals, the calculator uses 12 decimal places, and at the end, this is what the answer is. So actually, not only is the calculator easier to use, it's actually more accurate. 1.49 is actually the test statistic. So anyway, it lands right here, so it's going to be failed to reject, we proved nothing. Which is sort of surprising to me because I thought 36%, that's about 5% better than James. But based on the number of shots and based on only one season, when these guys play, well, professional players can play 15 to 20 seasons. You base it only on one season, that's not enough to prove that Bryant is better than James in the three-point shot. Okay, and then in Chapter 9, we also do confidence intervals at the same time. So here's a very vague example. Suppose you have two groups and the confidence interval looks like this. The difference between the percentages of the two groups is somewhere between 20% and 25%. Since both of these numbers are positive, then that means this has to be a big number, P1 has to be a big number, and P2 has to be a small number. And according to this, P1 has to be bigger, and it's got to be 20% bigger. So in other words, we could conclude that Group 1 has at least 20% more successes than Group 2. Whatever success means in this particular case, Group 1 is better at it. All right, here's the formula for the confidence interval. What you do is say, what's the difference between the two groups? And then there's got to be error. So subtract the error on this side, add the error on this side, and that is the confidence interval. And what's the formula for error? Here we go. It looks very similar to that z formula we did a minute ago, except instead of these being a p bar, it's p hat and q hat. And remember that q's always come from 1 minus the p. Or you can use the calculator, which is what I'm going to do. So here's a real-life example. Who do you think is more likely to pass one of my classes? Now this doesn't apply to all of Hartnell College or all colleges. This is just my own personal teaching data I've kept for years. So over the last many years, I've had 626 statistics students, and out of those, 530 passed with a C or better. During that same period, I had 505 calculus students, 359 passed with a C or better. So here's the data. Out of 626, 530 that's 84.7% passed. Out of calculus, it is 71.1%. So statistics is going to be Group 1. They have the higher percentage. So I am going to use the calculator. You go over to tests, and then you have to move down, 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 not over. I said down, 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 until you get to two proportions, because there's two groups. We're doing proportions, and you only have a choice of z. So you type in the data, and here's a case where, like I said, the n is written first and then x, but you have to type it that x is first and then n. Do the same thing for the other group. The confidence level is 95%. And then here's the interval. So look at, you should double check. P1 is 847, yes. P2 is 711. You notice my sly advertisement for 7-Eleven, the store 7-Eleven? Yeah. Anyway, so this is the interval. So in other words, the difference between the two groups is at least 8.7%, maybe as high as 18%. So that means that whoever group number 1 is, they're at least 8.7% better than group number 2. So that means that the statistics students have at least an 8.7% higher success rate. So if you wonder, hey, I need a college level math class, I want to pass, which one should I take, statistics or calculus? Definitely statistics. Although calculus is fun, don't get me wrong, calculus is very fun and useful. All right, the last part is, with a confidence interval, how do you get like fail to reject? When we do hypothesis testing, if the test statistic does not land in the tail part, we say fail to reject, we didn't prove anything. But what would that look like with a confidence interval? All right, here's some data that I just made up. Group number 1 has 400 out of 500 successes, or in other words, 80% successes. Group number 2 has 78.2% successes. So this group is approximately 2% better than this group. And it's based on 500 and 500. It's based on 1,000 people. Would we be able to prove something? Well, look at the confidence interval. So I skipped ahead and went to where you type in the data, make it 95% level of confidence, and then notice that it goes from negative 0.032 to positive 0.068. This is extremely important. When one side is negative and one side is positive, that means there's no difference between the groups. There's a few ways you could look at this. One is, what's the one and only number that lands between negatives and positives? You're right, 0. 0 is the only number that lands between negatives and positives. That means that P1 minus P2 could equal 0. If you then move the P2 to the other side, that means P1 could equal P2. In other words, the two groups could be the same. But that's only 1 out of 3 possibilities. This side says you have a positive number. If you have a positive number, it must be that this is the bigger group minus the smaller. So a bigger percentage minus a smaller percentage gives you a positive. That means that P1 is the bigger group. Excuse me, the higher percentage group. That already contradicts what we just said, because we just said that it's possible that the two groups are the same. Then this side is saying, well, it's possible that P1 is the better group. Then we have a negative on this side. Well, what's the only way you get a negative? It's from having a small number minus a big number. That means that P2 has the bigger group, or the bigger percentage. Now this is, once again, contradicting, because now this side, this is telling us, when this is negative, this is telling us P2 is the winner. When you look at this side, it says, no, P1 is the winner. And since 0 is in there, it says they're the same. So basically this confidence interval says 3 different things. P1 is better. No, I mean P2 is better. No, I mean they're the same. So, in other words, when you have a negative on one side, positive on the other side, it's the same as fail to reject. We did not prove anything. And that's the end of section 9.2. I'll see you soon in 9.3.